Hello again and welcome back. So we are still on chapter 3 and I finished the first lecture on chapter 3. So this recording will finish a few theory points and then we'll get into some examples and problems. Okay. So this is where we left off. I introduced you to the three primary orthogonal coordinate systems that we will be learning in this course, the Cartesian, the spherical and the cylindrical, and you can actually convert between them. So any point can be represented by any one of these three systems, and let me expand this. Okay, on slide 34, you see the nice little chart that gives you the conversion method, right? So, for example, if you want to go from Cartesian to cylindrical, now remember Cartesian or rectangular, everything is in x, y, z. So, to convert to cylindrical, which is in r, phi and z, the z remains the same. The r can be derived from the x and y like this, and so on, right? Similarly, for the unit vectors, you need in the cylindrical system, so you need the r hat, the phi hat and the z hat, and here's how you get them from x and phi. You need a knowledge of the angle phi, which you first derive as tan inverse y by x. Similarly, last thing you need are the three components uh, along the three axes. So you need, just like you have ax, ay, az in the rectangular system, now you need ar, a phi, az, and this is how you get them. So the same thing applies to the other conversions also. So this is important from an exam test perspective. So we need to learn how to do this, and I think once you do a problem or two, you'll understand the method a lot better. Okay. So here's just a description of the what is in the table. The derivation, some of the derivations are given, some you just have to accept them, but all this information is in the textbook. Now you can also see Cartesian to spherical, for example, spherical meaning capital R, theta and phi, and so that conversion also is shown here, and you can see the figure that tries to explain how the x, y, z converts to r, theta, phi. So you can see, for example, y is r sine phi. So, phi equals sine inverse y by r, right? So in that way you can convert between them. All right, like I said, unless we do some problems, we won't quite understand it. And we have some problems here, examples and problems. But we'll come back to this. Give me a couple more minutes to finish a couple of other theory material that's also in the chapter. So here, for example, there's a distance between 2 points is a topic. So I think we have seen this before, maybe when we did the position and distance vectors. We said that the distance, the magnitude of the distance is the magnitude of this vector from point 1 to 2, which you do it in this fashion in Cartesian, but you can do the same thing in cylindrical and spherical, and there are different formulas to do that. Okay, all right, so that was that. Okay, so that kind of finishes uh, vector algebra for the moment. Now we get into a topic called vector calculus, and of this, the basic vector differentiation and integration is the material that I kind of put together from other sources. The rest of it is actually still in our textbook. We'll just go back to it in sections that we have already completed actually. So we may go back to those sections, but the first two are kind of, and they are very easy stuff. You probably know it, but I wanted to bring it in to review before we start jumping into advanced calculus stuff. Okay. So here is some drawings and some material from another textbook. So it's written slightly differently. Again, for example, I, J, K are the unit vectors here instead of your X, Y, Z, that we are used to. And another thing you'll notice is we are now writing the vector, and that vector is for this curve, which is in 3 dimensions. And that curve is written, it has a basic equation like this, right? R as a function of u, which is an independent variable, and it could be time or some such thing. So R of u is written as a function of u x with the unit vector I, function of y with the unit vector j, and a function of z with the unit vector k. Okay, I, j, k are here. So if this is the function of this particular vector, and it travels right along that path, then the derivative is defined like this. So that's what I wanted to introduce to you. So you can take a derivative of this vector and you get dr by du, and it basically is the derivation of each of these, and you retain the ijk. So the differentiation is also a vector. That's the point I wanted to make. Now there are rules and laws, and there's actually a lot of formulas for the derivative of the scalar, the derivative of the sum. I'll leave it up to you to find those in various sources. I just gave you the top 3. Maybe you're already familiar with them. I hope you are. But here's a summary of some formulas. Similarly, so far we have only talked about one variable, right? U. But you can have vectors in many variables, x, y, z, for example, 3 different variables, more than one scalar. Then you start getting into partial differentiation, right? So if this vector is differentiated with respect to x, y, z, each of this is a variable, then you write it like this, and then there are some formulas and rules for partial differentiation of, like, the scalar product of 2 vectors, the vector product of 2 vectors, and the second derivative, and so on. So here are some rules, right? Okay. Then, so that was really my introduction to vector differentiation. I don't want to go too deeply. We'll have plenty of time to do problems and learn more, but that was a very brief introduction, and I hope that was helpful. Similarly, I have one slide, just one slide, and then we'll do a problem each on differentiation and integration. But here's some basic material on vector integration. So again, you have a vector which is a function of u, an independent variable, and is written as r1ui, r2uj, r3uk in a 3-dimensional coordinate system where I, j, k are the unit vectors. How do you do an integral of such a vector? So you can take the I, j, k, it is going to result in a vector, right? But the ij can be taken out, and you integrate each of these quantities which are a function of u with respect to du, right? Now assuming that an integral actually exists, remember we know a lot of functions that cannot be integrated, but assuming that a derivative exists that satisfies this, then how do you find that? So let's say s exists such that Ru, this given function, is a derivative of s. Then basically what we are saying is, to find s, we integrate Ru, right? So that is, Su is the solution to integral. So to rewrite this, you can say integral of Ru du is integral of the derivative of Su, which means Su plus a constant, right? Now similarly, integrating from, this is an indefinite integral and this is a definite integral. So to go from a to b, you integrate like this and you end up with something like this. So what does this mean? We have a nice little problem that we'll come back to, and we'll learn more about vector integration. Okay? All right. So that is the theory material. Now I have to do a whole bunch of problems for you, and hopefully I can get through most of it. So let's see. Let's start with, I'm going back, by the way, in slides. I hope to find example 3.1, which is from your textbook, and I'm on slide 18 now. So this is the most basic thing that we have learned in this chapter, and so there's example, the first example on page 138. So we are given 2 points, P1 and P2, and we are asked to find a bunch of things. Vector A, for example, goes from the origin to P1, and so you have to find how to write that vector, its magnitude, and how to calculate the value of the unit vector along A. Then the angle between A and Y, vector B, the angle and the perpendicular distance from the origin to vector B, which is this distance, right? So I won't spend too much time. We don't have time to spend. I'm going to have to leave it to you. Please, please, please read the example carefully, understand it. It's a very simple mathematical problem. I'm sure you can figure it out. Mathematical and trigonometry. So the only thing that may be a little difficult is this part E, which is to find the perpendicular distance from the origin to vector B. And to do that, you actually have to, he creates a little triangle here to give us the angle between the origin and, sorry, this distance from this triangle is the magnitude of A times sine of this angle, right? Now that angle is 180 minus theta AB. So that's the only slightly tricky part, and we calculate theta AB here in part D. So using all that, you can see how the problem was solved. Okay, it's a basic problem, but if you don't understand this, everything else is going to be hard. So take your time making sure you follow each step and you understand it. I can only say so much about that. Next example 3.2 similarly is from the textbook. I don't want to spend too much time on this. You're given ABC and you have to find the triple. Well, basically he's trying to make you prove that A cross B cross C, oh sorry, A cross B and then cross C, which is a cross product, is not the same as A cross B cross C. Because when it comes to cross products, the order is important. Okay, it's not so important for the dot product, but it's important for the cross product. So learn how to do this from following the example in the textbook. Okay, all right. Now I have some other problems from elsewhere and from the back of the chapter. I think you'll benefit more if I spend more time on those. So the first of these problems, I just call it a distance vector. 2 points are given, their coordinates are given, and we have to calculate the position vector P, the distance vector from P to Q, the distance between P and Q, and a vector parallel to PQ with a given magnitude. Okay, so let me walk you through the solution. Okay, so here it is. It's in my file. It's a PDF file. I post it online and you can retrieve it. Page 1 of my PDF file. So the 2 points are 0, 2, 4 and minus 3, 1, 5. The position vector R from origin to P is nothing but R1 equals, or this x times 0, that's the x coordinate, y times 2, and z times 4, which is this. Now the distance from P to Q, we use this formula, vector PQ equals R2 minus R1, which you can actually do this. Here's a neat way I learned from somewhere else. Just write the coordinates and subtract them and then convert them into a vector form in this way. Okay. Similarly, the distance between PQ is the magnitude of this vector, which is like this, and it's this value 3.317. Now the vector parallel to our PQ with a magnitude of 10, right? That's what we need to find. Now that's a little bit tricky. So write the required vector as A equals this, right? Where A, the magnitude, the scalar magnitude, this is given to be 10. Since A is parallel to RPQ, A is the same as the unit vector of this, right? Because we want them to be parallel. So the unit vector is showing in the same direction. So A, which is the unit vector of the new required vector, that you just calculate based on the original vector, right? Which is RPQ, the line that connects P and Q. So take the original vector divided by the magnitude and you will get a vector which is the unit vector. Then you can write the required vector, which is parallel to the other vector, as the magnitude 10 times all of this, right? Now remember, this is a vector, which is this unit vector. So if you do that, then the required vector comes out to be like this. Okay? I hope that was clear. I hope you know what I did here. First you have to divide by 3.3 and then multiply by 10, and you should get this. Okay? All right. If you have any questions, of course, you can ask me, but it's a pretty elementary problem. I found it somewhere else though, by the way. Okay, here we have a problem from our textbook, problem 3.5, 3-5. Given these vectors, A, B, C, find the following. A and A, unit vector A, component of B along C, the angle between A and C, A cross C, A dot B cross C, A cross B cross C, the unit vector cross X cross B. X is the unit vector along the x-axis, so that unit vector crossed with B. And finally, A cross Y dot Z, the unit vector. So a bunch of things to find here. So let me quickly show you how to do most of it. Pretty easy. I think you'll agree that the mathematics here is not too difficult, but you just have to know how to deal with vector quantities with all these coefficients and unit vectors and all that. Okay, so find A and A prime, right? So magnitude of A or A hat. Magnitude of A is this, and A hat, which is the unit vector, is you take that original vector divided by the magnitude and you get a unit vector. Okay? Now if you take the magnitude of this vector, you should come to 1, right? That's why it's called a unit vector. The component or projection of B along C. So to do that, we use this formula, BC equals B cos theta BC, right? This is a component is a scalar quantity. If nothing is said, you assume it's a scalar. Sometimes they'll say find the vector component. Then you have to go to the vector form, okay? But this is scalar, so we do this. There's a couple of formulas, but I'm using this method. So BC, the component along the C axis is along C is B scalar product of AC, which is the unit vector along C. Okay. Now, what is the unit vector along C? It is C by magnitude of C, right? So this is what you get. Then BC from this formula becomes B, the given vector, times C, or times A hat C, which is the rest of this. So if you solve for that, you get a nice quantity of minus 1.8. Okay. All right. Moving on, theta you calculate as the cos inverse of something, and you can see this is the way to do it, and it comes out to be 17 degrees. A cross C, you have to use the determinant method. So see how it's written. I've tried to be as clear as possible so you can follow along. XYZ, AX, AY, AZ, CX, CY, CZ, and you get this vector. A scalar product of B cross C gives you a scalar, so that comes out to be 20. A cross B cross C will be a vector again, it's a triple product, and so to do that, first you calculate the inside, which we just did. Maybe we didn't do. I guess I did it here. B cross C. Oh, it's here. B cross C. Yeah, I think we did it somewhere. I don't know where I got that from. But anyway, B cross C is here, and so A times A cross B cross C, you do it in determinant form again. Then we have G and H, X cross B. See how that I did that again using the determinant method. Lastly, a scalar product, this times Z, you can see how it comes out to be 1. Okay, so please make sure you go through each of these steps also carefully, and you understand how to do simple cross and dot products. Okay, all right, let's go back and look at problem 3.7. So here you will notice for the first time that we have a problem where the coefficients are themselves functions of the variables x, y, z, right? So this is not a constant vector, it's a non-constant or non-uniform vector, okay? So given such a vector, determine a unit vector parallel to A at this point, okay? So that's the problem. Okay, so how do you do that? So you're given A, which is a function, and each of the coefficients is again a function of x, y, z. At point P, this A, so this is a function, right? It can result in hundreds of points, millions of points. But one point on this vector is given to us, 1, minus 1, 2. So as soon as you put that in, you get a definite vector A at that point, right? So a unit vector parallel to A at P, it has the same uh, right same direction. It's the same as the unit vector associated with A. And how do you find that? It's just A divided by magnitude of A, and you do that, you get the unit vector parallel to A. Okay, all right, I know it feels like a bit of a rush, but that's the way it is in this course. All right, 3.13. So here we are given a line, straight line equation, x plus 2y equals 4. You know, this is in the form y is equal to mx plus b that you're so familiar with from last semester also. So given line is described by this equation. Now vector A starts at the origin and ends at a point P on the line such that A is orthogonal to the line. Orthogonal meaning perpendicular. So if you draw a line from the origin to meet this other line given, and if they meet at a point where the angle between them is 90 degrees perpendicular, then find an expression for that vector which begins at the origin and ends on this line. Okay, so let me show you how that is done. So here's a drawing that shows you the original line and the line from the origin, and they have to intersect at this point. So first of all, I'm writing the equation like this. Now vector B, first I want to create a vector to describe the line, right? B. So vector B is from point P1 to P2. So there is a formula or there's a method to write that B in vector form. Now given this equation, right, we can say any point on this line can also be written in this form, right? For any point on this line, you can say, because y equals 4 minus x by 2, so in general x and y are written like this. So there's x, there's y from this formula, right, on any point. Now we need to find a point P so that the vector OP from origin to a point P, which can be written like this, right? We know how to write an equation for any line from point A to point B. In this case, point A happens to be the origin. So that vector is in this form. Now, if A is to be orthogonal to B, then the scalar product, the dot product, has to be 0. So if you write the dot product in this way, you have one unknown, which is x, and you solve for x, you get 0.8. Then A, which is this, right? You just put that 0.8 and open this up. You can get this form for the vector A. Okay. So A is this vector, by the way. So I call it OP, but OP is really that A. So if you take the 0.8 and put that in here, then and the same 0.8 here, you get the expression 2 becomes the equation, the vector equation for A. Okay. All right. I will go back to my next problem. 24. Well, I'm on slide 24. So we are moving into the Cartesian coordinates business. We just finished vector algebra problems. I'm going to give you some homework problems also. So with the examples, my problems that I showed you and what you'll do with your homework, hopefully you'll all become good at solving vector algebra problems. So let's look at coordinates business. And I'm moving ahead to slide 37, where we stop at example 3.7. Now there's a bunch of problems and material in the middle between example 3.2 and example 3.7 that is kind of calculus based. So after we finish this session, I will go back and relook at that material, and then we'll do those problems. Okay. So for now we are at 3.7, and we have 1 point and a vector. We are asked to express P1 and A in cylindrical coordinates and evaluate A at P1. Okay, so we are given Cartesian coordinates, we have to convert to cylindrical coordinates. So this is example 3.7. It's pretty straightforward. Let me look at my textbook and I will tell you where it is. Give me a second. Yeah, it's on page 149. Yeah. So on page 149, and basically all he does is he we are given the Cartesian coordinates, right? He uses the formula from the table to go from xyz to r phi z. Z remains unchanged, and he just plugs everything that we know about xyz to get r, to get phi as tan inverse y by x, and then for calculating a also, So that's the point P. Then calculating A also, he shows you how to do it, because now you need to find the cylindrical cylindrical components AR, A phi and AZ, and then once you get those using the formulas, you put it together to write an equation for the vector A in the Cartesian, in the cylindrical coordinate system. Okay, and then he plugs in at a given point P, phi is 3 or 6 degrees. So once you put that in, then you have a definite expression for A. Okay, so take a look. I can't spend too much time on that example because it's so nicely solved in your textbook. So let's move on to the next example, 3.8, which is on page 153. Here we don't have a constant vector or a uniform, but we have a non-uniform because these coefficients are again functions of x, y, z. So to convert from Cartesian, because you have x, y, z, into spherical now, okay, not cylindrical but spherical. So take a look again. It's a simple conversion. You have to use the formulas in the table. Make sure you understand where to look for in the table and how to solve this. It's shown quite clearly in the example, and I will skip ahead so we can do something that is not so well given to you, and that may be more helpful. So I'm going to skip to problem 323 from the back of the chapter. So 323 says, convert the coordinates of the following points from cylindrical to Cartesian, okay, which is kind of what were the examples that we just saw also. So how to do 323? So here it is. Convert from cylindrical, which is r phi z, to Cartesian x, y, z. So this is kind of going in the reverse direction. So you're given P1 equals 2 pi by 4 minus 3. So I'm using these formulas: x equals r cos phi, y equals r sin phi, and z remains the same. So P1 becomes this, okay, as you can see. And so what you get is in Cartesian coordinates x, y, z. Similarly, P2 is 3, 0, minus 2. There's P3, which starts with 4 pi phi in cylindrical, right, r phi z, and we get in Cartesian x, y, z using the same formula: x equals r cos phi, y equals r sin phi, and z remains the same. Okay, all right, so that was 323. Now we have a bit of a more complex problem that you might enjoy solving along with me, I hope. So a vector field is given in cylindrical coordinates by this formula. It's in cylindrical, okay. So it has r phi z, okay. So a point is also given on this, in this field, and that point is 2 pi 3, okay. So r is 2, phi, the angle is pi or 180 degrees, and z is again distance 3. So that point is located on the surface of the cylinder described by r equals 2. So if you take r equals 2, which is, this first point, you have the cylinder, and the other dimensions or the other coordinates of that P, I mean obviously 2 is given, so that's the r radius. The other are pi and 3, okay, so that's given. So at point P, find the vector component of E perpendicular to the cylinder and the vector component of E tangential to the cylinder. So you have this cylinder and we need to find a vector component of E perpendicular to the cylinder and also tangential. Okay. So what does all this mean? Perpendicular, tangential. So I had to go in and create an extra notes, some notes for you so we can solve this problem. So here are some notes, okay, on the next slide. That's why I put a note here saying see next slide, okay, when you solve this problem. So we are on slide 41. So here is a surface and this vector, so the vector V is kind of describing this surface or field at this point. It has a perpendicular or orthogonal uh, component, well, normal or perpendicular, not orthogonal. So this component is perpendicular or normal to the surface, and this is called tangential. Okay, so these two, any vector has this too. So an important rule to remember is any vector V can be resolved into two mutually perpendicular components. Okay, I guess I should write mutually perpendicular components. That means they are perpendicular to each other. And you can add them and that gives you the original vector. So where this is normal to a given surface and this is for a surface, right, or a field, and the other one is tangential. How do you find these components? Here's a bunch of equations that will help you. So the normal or perpendicular component, which is this component, is a scalar product of the original times the component, the unit vector in that direction, right? That's what this n means. So in that direction that you are interested in, you find the unit vector and you take the scalar product first, v dot n dot product, and then you attach the unit vector sign to it, so it becomes a vector. Similarly, the tangential one is now given in this way, minus n into this cross product, or because the two add together to the original vector, you can also do a simple subtraction to get the other tangential component. Okay, so here's another drawing also to tell you, if you have a given field, what is the normal vector or perpendicular vector and what is a tangential vector. Okay, so I hope with this description it helps you to solve this problem. Okay, so let's go to 328 and see how exactly it's done. So you're given E, which is like a field or a surface. The perpendicular vector component, say En, you get it from this product like I just showed you. Take the unit vector in that direction, which is actually R, this direction, which is in the perpendicular direction to the surface, and you do, well, first you do a scalar product and then you attach the unit vector to it. So how to do this? Here's how I show you how to do it. And so you end up basically with just this component, right? Everything else becomes zero when you do a dot product, because you have to multiply this with each of these, right? And since R, or this R hat, doesn't have the other components to multiply. Remember how you do scalar product, right? You have to take each of the coefficients on both the A vector and the B vector and multiply them individually. If the others two are zero, then you are only left with one, and that is what you get here. Now at a given point, this En, the perpendicular component of that vector, becomes this. Now how do you get the tangential component? Here I am taking the easy way out by just subtracting from the original, and you get this. At point P, 2 pi 3, this becomes, you just substitute r, phi and z, and you get the ET as a vector 9 with in this direction. Okay, so that may be a little complicated, but I hope with my notes and all that you are able to understand. So here are a couple more problems. Let's see, do I have time? Okay. 329. At a given point in space, vectors a and b are given in spherical coordinates by a and b. Find the scalar component or projection of b in the direction of a, the vector component of b in the direction of a, and the vector direction of b perpendicular to a. So three things to find for a pair of vectors a and b. Okay, so that's problem 329, and here's my solution. So a and b. So projection means just a scalar product, right? But to find that, you have or use this formula, right? B hat into a hat. So unit vector a is this, right? This by root 21. Projection BA is this. Actually, this is not a hat, it's just B, right? I should not put a hat there. Just remember that, right? This is also not a hat. Jeez. It's a straight line, not a hat, and similarly, it's a straight line. Okay, okay. I hope that removes the confusion. So you do the product of this times a hat, and so you end up with a scalar quantity minus 2.4. Now part B says find the vector quantity, right? Vector component. There the method is slightly different. So you have to do this way. And so BA, the vector, comes out to be this. Okay. Now the vector component of B perpendicular. Now this was in the direction of A, right? Vector component. Here we are being asked to do the perpendicular, so we once again use that formula. B equals, the perpendicular or the normal component plus the tangential component together gives us the original. So we just found the tangential component, which is the direction of A, then the perpendicular component is the difference. Okay. All right. I have one more problem from just this Cartesian coordinates, which I'm probably going to skip because I want to get to the integral problems. So take a look at 333, and if you have any questions, let me know. All you're being asked to do is to transform this vector. Unfortunately, the vector is not a simple constant vector, but each of the coordinates is a function of, again, the parameters theta, phi, and z, or r in this case. So transform that vector into cylindrical coordinates and then evaluate it at a given point. So take a look. If there's any questions on that, you can definitely reach out to me. So let's move on to doing a couple of the calculus problems, and then we'll finish this recording. So here we talked about this, right? Vector as a function of an independent variable u or t, as I said, and then how to do the differentiation. So that's what we are trying to practice here. So a particle moves along a curve whose parametric equations are x, y, z. So remember this term, you might run into it often. What that means is this curve has these three components x, y, z, that define how the curve is behaving. So given this, determine its velocity and acceleration at any given time, that means create a general expression for the velocity and acceleration, which are both going to be vectors. find the velocity and acceleration at t equals 0. So these are the two things to do. So let me quickly go to that problem. Okay, here's how to solve it. So you have xt, yt, zt. The first thing you do is to write the position vector r, which is like this. So x into xt plus y into yt plus z into zt. So it becomes this, right? Now velocity, you differentiate it once, which means you take the derivative of each of these. Remember, nothing to differentiate. This is just the unit vector. So just keep that aside and then take the derivative of this, the derivative of this, the derivative of this, and write it in this form. Acceleration is the second derivative, right? So you differentiate this and you're going to get this, another vector. Now at t equals 0, so in these equations, you substitute t equals 0, right? And you get this. And you can also find the magnitude as the magnitude of this vector as this. Okay? So I hope that was clear. That's important that you learn this. I don't have, maybe I'll give you a practice problem on this also, a homework problem. But if you have enough of this background, then we can start tackling more advanced calculus in the chapter. We have plenty more to do in calculus, but this is at least the basic you need to know before we begin to do this. So here's another integration problem. You have a given function, a vector in u, and each of the coordinates also is a function of u. So given this, find an integral and find a definite integral. Okay, so let's take a look at that and we can close the chapter. So here is the function. Integral just means you integrate the whole expression with respect to du because it's a function in u. So take the hats out, x hat, y hat, z hat comes out, and then you apply the integral to each one individually, right? It's a simple integral here, not very complicated. So u becomes u square by 2, u square is u cube by 3. There's always a constant that you need to keep in mind. So each of these three terms becomes this after integration, and then you can club them together, put the c1c instead of the c1, c2, c3, and you write the vector of the integral in this form. Now if you want to apply limits to this integral, then you can take the same result, put 1 to 2 as the integrals or as the limits, and then you first, you know how to do the first apply the upper limit 2 to this u, then the lower limit, and you take the difference, and then you end up with a vector that looks like this. Okay? Alright, so that brings me to the end of this recording. I apologize, I went 4 or 5 minutes over, but when we come back in my next recording, we certainly will hit some real hard calculus immediately, and I'll tell you that for the rest of the course it's gonna be calculus, calculus, calculus all the way. So be prepared. Of course you still need vector algebra also, so you can't afford to forget that. But I hope this was a good beginning to chapter 3 and the rest of the material. Take some time, go through the examples, go through my problems, do the homework by yourself. That's the best way to learn. Don't just find some solutions somewhere on the web or from your seniors and say, I'm just going to copy. No, the homework, if you do it, you're going to learn the material and be better prepared for quizzes and exams. Okay? All right, with that, I will stop and we'll continue chapter 3 theory in my next recording. Bye.